So here's our definition from the previous video, average speed. Let's go ahead and do an example with this. So a rock breaks free from on top of a cliff. What is this average speed between 0 seconds and 2 seconds? 0 seconds when it breaks free and 2 seconds after that, and from 1 second to 2 seconds. So just recalling from the previous video that our motion is going to be y is equal to 16 t squared feet. This is our approximation here. And y is distance fallen. So if y is 5, that means it's fallen 5 feet. You could put on a negative sign if you want to interpret it in a slightly different way. We'll go with this version here. So let's just go ahead and use this formula right here. So we want f of 2 minus f of 0 divided by 2 minus 0. So that would be, I guess here, we'll go with y of 2 minus y of 0 divided by 2 minus 0. And so this is going to be, plug in 2 into here, we get 16 times 2 squared. Plug in 0, minus 16 times 0 squared divided by 2 minus 0. And when you crunch this out, you get 32 feet per second. So the average speed between 0 seconds and 2 seconds, 32 feet per second. Now let's do the same thing between 1 second and 2 seconds. So now it's y of 2 minus y of 1 divided by 2 minus 1. Y of 2 is still 16 times 2 squared. Y of 1 is 16 times 1 squared divided by 2 minus 1. And this crunches out, crunch, 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 as 48 feet per second. Okay, so the average speed is higher in the time from 1 second to 2 seconds, 48, than it is the time from 0 seconds to 2 seconds, only 32 here. But we might also try to answer the following question, which is, what is the speed, not average speed, but what is the speed at t is equal to 1 or t is equal to 2? Well, right now, at this moment in our calculus class, we don't have a way to exactly compute this. The best thing that we can do is, so I'll say here, can't compute this right now. So the best we can do, we can try to compute average speeds on smaller and smaller time intervals. So, for example, let me just draw a number line here. So, here's 0, here's 1, here's 2. We just did calculations. The average speed where t0 was 1, t1 was 2. We did the average speed on this interval. We could decide, okay, well, make this 1.1. Shorten up the time interval right here. So average speed on 1 to 1.1 is going to be, so y of 1.1 minus y of 1 divided by 1.1 minus 1. Y of 1.1 is 16 times 1.1 squared minus 16 times 1 squared divided by 0.1. And this crunches out as 33.6 feet per second. And okay, we did this on the interval from 1 to 1.1. Well, we could do this on an interval from 1 to 1.01, or the interval from 1 to 1.001, or, make that smaller and smaller and smaller. We could do any of those calculations. We could keep making that, the length of the interval smaller and smaller. And so I've pre-computed all of this stuff. The average speeds over short time intervals from t0 to t0 plus h, where t0 is either 1 or 2. And our formula here is change in y over change in t. t0 plus h minus t0 will be h. And then the 16 times t0 plus h squares, that's y of t0 plus h, minus 16 t0 squared, that's y of t0. And so here you can see all of these things that we've calculated. So when h is 1, the average speed, using t0 is equal to 1 is 48. That was actually this calculation right here. When h is 0.1, 33.6 feet per second, that's right there. H is 0.01, 32.16. Then 32.016, 32.0016. Okay. We can also do the same thing for t0 as 2, and check for yourself at home that you get. Let me slide this up so you can make sure you see all of this stuff. Check for yourself that you get all of these answers as well. Okay, let's take a moment and just try to think about what's going on here. 48, 33.6, 32.16, 32.016, 32.0016. What behavior is going on here? Well, as h gets smaller, this seems to be getting closer and closer to 32 feet per second. And as over here, as h is getting smaller, 80, 65.6, this is getting closer and closer to 64 feet per second. Okay, so this is what it looks like that's going on. Is there a way for us to do this, again, let me adjust the video so you can see that there. Is there a way for us to be able to prove this? Well, let's think about actually crunching this out. So our expression here, let me just copy this. The change in y over change in t was 16 times, let's do t0 is equal to 1. Let's do that case. So 16 times 1 plus h quantity squared minus 16 times 1 squared divided by h. Okay, simplifying this, we get 16 times 1 plus 2h plus h squared minus 16, all of that over h. And if we distribute out the 16 plus 32h plus 16h squared minus 16, all of that over h, and I'm getting excited because there's cancellation that happens, and that goes away. And upstairs, our two remaining terms both have h as factors of them. So let's pull out a factor of h times 32 plus 16h divided by h. Cancel, cancel. And so this ends up as 32 plus 16h. So first off, let me just say here, this expression here, 32 plus 16h, if you go through and plug in h is, say, 0.001, plug it into this, you will get exactly 32.016. So this checks out. And then the thing is that if h gets really, really close to 0, this goes away here, and we're just left with, so I'll just say as h goes to 0, the average speed goes to 32 feet per second. And so we want to be able to come up with a way to more precisely define this to get that the average speed at t is equal to 1 is exactly 32. I'll let you do the t is equal to 2 case yourself. I think it's an instructive thing to do here. And this process here is our first look at, doing limits down here. We can make this more formal. Chapter 2 is all about limits. But this is our first example of a limit, and this is actually going to be in chapter 3 how we take the derivative of a function. We just have to develop the tools to formally take limits and formally calculate derivatives. But this sheet and the previous couple sheets give you the idea of what's going on. Okay, so this is a very important video, just kind of showing you how we go from tables like this to thinking about average speed. It sets us up for things we're going to do in the future.